And hello, welcome to this video on turbulence modeling. We're going to continue discussion on IDDES models and DDES models. Before I continue, I want to make a correction to something I said in the last video. In those, I said that the expression for RD equals to max of 0 and the magnitude of this velocity gradient. Now this is kind of incorrect, because in the paper it should be 10 to the minus 10, because the whole idea is to prevent the denominator from going to 0. So yeah, I think I made a little mistake here, but the intent is still the same. You don't want the denominator to go to 0, so you put a 10 to the power minus 10 there, so that you have a floor. Okay, it doesn't go below 0, or it doesn't go to 0. Okay, so everywhere you see this RDL, you should have this limiter at the bottom. Okay, here also. Okay, so this should be it for Spalart DDES model and IDDES model. IDDES especially, where you have this thing in the denominator here. It's just something to make it more numerically stable. Now, I want to move on. Hopefully that's the last careless mistake I have made, but yeah, if you see anything else that's weird, just post something in the comments and I'll try to respond and take a look. Yeah, if I have the time. Anyway, so yeah, we want to move on to discussing two new models today. They are just the K omega SST adaptations of IDDES and DDES. They are from this paper called Development of DDES and IDDES formulations for the K omega shear stress transport model, the K omega SST models. So you should be able to download this on the ResearchGate using this link. On the ResearchGate, you should be able to download a full text. You should be able to download the full text from here in this link here. So you say download full text, and you should be able to see the paper in its entirety. I will also I'll refer to it every now and then, but I do encourage you to download the paper, especially if you want to see more of the model details. So yeah, do take some time to download the paper, because I'll be referring to it a lot. Next, I also provide you the link in Springer. This is where the article is published. And then also, here are some of the links I'll paste in the description for the K omega SST DDES and IDDES OpenFoam source code. So both of these will be in the description. You see the K omega SST DDES. Oh, Spalart IDDES. Okay, I'll need to change that. Yeah. Okay, so it's in the turbulence models DES. If you look at this part, it's in turbulence models DES, K omega SST IDDES. So copy and paste here. Alright, and that should give you the correct models. Alright, so this is the correct link. I'll copy and paste it inside the video description. So do take a look. And so when I mean video description, I'll give you my example. Over here I have the Spalart IDDES video. Just posted it. Okay, so the description is over here. You'll see just below the video. Click show more and you'll see all the resources available for you. I'll paste it all here. All the references, links, useful stuff. Do see it here. Okay. Alright, so all this will be pasted in that section below, along with some other useful links. Okay. So yeah, without further ado, I'll start. So how do you develop the DDES formulations for K omega SST? So recall the K omega SST DES, Detached-eddy simulation formulations, where the only modification is that you kind of change this destruction term in the K equation, the turbulent kinetic energy equation, and you give it a DES length scale, or a DES length scale. So this is this is the Rand's length scale, if I'm not wrong, and this is the LES or DES length scale. Yeah, that kind of length scale. Okay, so your K equation can end up looking like this, and your omega equation, you kind of just let it remain untouched. Okay, for DDES, there are a few changes you need to make. Okay, not just well, you'll change. There are some constants that need to change, but let's give you the overview of some of the most important changes first. Firstly, you have a length scale change. So LDDES, okay, equals to LRENS minus FD. Remember, this is the delay function. Then you have a max again. This is very similar to the Spalart amorous formulation. So we have LRENS here minus LES. Okay, simple enough. Okay, what's the LES? The LES length scale is CDES Hmax. Okay, Hmax, which is the maximum. It's the maximum length of your cell if it's a orthogonal cell, especially. If it's weirdly shaped, I guess it can be the longest side. But no, this is equivalent to CDES delta. That is if delta equals to this Hmax anyway. So yeah. So for very skewed cells, cells with very long length and short width, this definition is important. If your cell is more or less like a cube, or even a distorted cube, but more or less the lengths are the same, then the length scale Hmax would also be the same as a cube root volume kind of a formulation. So it doesn't really matter. This Hmax only matters if your cells are very elongated. Alright, anyway, so as I was saying before, we have a LRENS equals to, alright, something like this. Okay, K is 0.5 over omega, where omega here is equivalent to K divided by epsilon over K. Epsilon divided by K. In the literature, you will see LRENS equals to this. K omega 0.5. Then you have a C mu over here at the bottom. Okay, this is, I denote this omega star, okay, because how do you define omega star? Okay, you see my videos, I'll define omega star like this. Omega equals to C mu omega star. So sometimes in turbulence modeling textbooks, again, you'll see omega equals to this epsilon over K, but sometimes they multiply this C mu in. So whenever the thing is multiplied by C mu, as you see in literature, I will try to say omega star here rather than just omega. So so this is actually why I denote this omega equation, omega star. So it looks exactly like what you would see inside the how do you say? You will see like those inside the literature, but just to hopefully prevent confusion, I just define omega like this and omega star like this. Okay, so omega star equals to omega over C mu. That's all. Okay, just want to be very clear on this definition, and just be clear on what LRENS is. Okay, so maybe I'll just use this one in future. So it ends up that your equation can look something like this. Have this here, and yeah, just a substitute copy and paste kind of an idea. Okay, and of course, what is CDES? CDES here. Okay, again, it's a blend between two CDES constants. One applies for one is calibrated for K epsilon model, one is calibrated for the K omega model. That's why you have this blending function here. This was covered in DES videos, K omega SST DDES videos, so I'm not going to go through this again. But just remember, this CDES will cover it will be calibrated for two constants, one for the K omega part, one for the K epsilon part. So it's a blend of many models. Now we want to talk about the more important part, which is the DES part or DDES part. Okay, the blending function here. Okay, it is defined as the following. Okay, it's defined as the following. It's equals to 1 minus hyperbolic tangent. All right. C d1 r d to the power of c d2. Okay, c d2. Okay, inside the Spalart amorous DDES model. Okay, if you recall, fd is equals cd1 will take a value of 8, cd2 will take a value of 3. Okay, but in this paper, okay, this is kind of altered slightly, so that you will have it's just altered to match experimental data, especially I guess in the log layer. Okay, or rather it's here to calibrate FD to prevent onset of LES in boundary layer. Okay, that's all FD here is supposed to do. Okay, FD is here to prevent the onset of LES in boundary layer, which is the intent of DES and DDES. So they changed the CD1 here to 20. So just take note of that. CD1 equals to 20. RD here will take the same form as before. And you have this formulation here. Okay. This is from the Spalart amorous version. Oops, sorry. Spalart amorous version. RD is as such. All right. This is the SA DDES model. Okay. This is from the SA DDES model. Over here in the literature, you will see this equation pop up. Okay, so the numerator is basically the same. Denominator is basically the same also. This is the distance from the wall. This is the von Karman coefficient, 0.40, 0.41. This, you will see this expression show up, 0.5 s square plus omega square. So hopefully you're familiar with this. This is the mean rate of strain. This one is the vorticity tensor that's got to do with the vorticity. This is the magnitude of the vorticity tensor. This is the magnitude of the strain rate tensor. So it's kind of written slightly differently from this vector notation, but more or less they are here to kind of mean the same, very similar things. So there's a slightly different way of calculating RD here, but the idea is just to prevent onset of LES in the boundary layer. The intent is exactly the same. Okay, so you won't see the max blah 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 over here, but this formulation tends to work well, and it's similar enough in concept. So yeah. All right. So what are the model constants? Okay, C mu equals to 0.09. Kappa equals to Kappa equals to 0.41, and A1. Okay, there'll be a constant in the paper. It says A1 equals. Okay, never mind. I'll just skip that. It's kind of repetitive. I'll leave that. Okay. So these are the important bits. CDES1. again it will be 0.78. CDS2 equals to 0.61. Okay, CD1 equals to 20. CD2 equals to 3. So all these are more or less the same. Just take note of this new RD function, and CD1 equals to 20. So basically, again, this FD is the delay function to prevent onset of LES inside the boundary layer. Other than that, all your constants are the same with the K omega SST DES model. Okay, nothing too new there. Now let's go to the IDDES version. Okay, so they in the paper they just performed a series of tests, and again we just simply changed the length scale. The formulas are pretty much the same except for the length scale. The length scale over here, right? This is the length scale. Alright, this is where you replace your length scale with DES, DDES and IDDES. That's all the changes you're doing. So IDDES, again the formulation is pretty much the same. You have F D tilde. This is very similar to the Spalart amorous version. 1 plus FE. Okay, so this is to correct the log layer mismatch function. Okay, LRENS plus 1 minus FD tilde LLES. Okay, that's all. This is what your IDDES model looks like. And LLES again is the same. You have this function here, same. LRENS is the same. So just copy and paste this over here. Just keep in mind what omega is and omega star is, because in the literature you'll see that doesn't have a star, but I use a star here. Okay, DES or CDES is exactly the same. Okay. All right. So this LES actually, yeah, LES is slightly different. Sorry, like that. The LES length scale is slightly altered because there is the wall model being blended into this. So this delta here will be defined slightly differently. So delta equals to min, okay, CW times the max of DW Hmax. So Hmax makes a reappearance. Okay, DW and Hmax and Hmax. So I'll just copy and paste this here. Yeah. So this filter width is slightly different from what we have before. I think yeah, just made a blunder there. But yeah, it's here to tell you, okay, I'm blending between the wall model LES and the Hmax. So that's, and yeah, wall model LES and then DDES. So that's why it likely will be slightly different, this length scale. Okay, so that's why. Okay, now on to FD tilde. Okay, FD tilde again is defined slightly differently. Okay, 1 minus FDT close and FB. Remember this length scale corresponds, or rather this part corresponds more to the DDES. This part corresponds more to the wall model LES, right? Okay, so FDT is defined very similarly as before. FDT equals to, okay, FDT equals to the following: 1 minus hyperbolic tangent, and bracket here, okay, C dt 1 R dt to the power of C dt 2. Okay, so C dt 1 again is 20, CD22 is 3. There are some comments about it, but I'll get to that later. Okay, FB will take a very similar function form to what we have, but just take note here, it's 2 exponential minus 9 alpha square. Okay, and then I have 1.0 here. So this is again supposed to go between 0 and 1, and this is taking care of the wall model LES part. Again, alpha is the same as before, 0.25 minus dw, okay, dw divided by hmax. Okay, and there we go. Alright, so that deals with the FD bit, FD tilde bit. We still need to deal with this FE bit that takes care of the wall model, the lock layer mismatch. So I'll carry on in the next video. Thanks for watching. I'll see you guys again. Bye bye.